Welcome back everyone. In this lesson we are going to learn about complete Gaussian elimination method. In the last lesson we have learned about the naive approach for the Gaussian elimination method, and we have seen that there are certain pitfalls for that naive approach. There are some certain problems that we are going to face in practical problems that make the naive Gaussian elimination method a failure one. So in those cases the naive approach is going to fail. So we need to incorporate some of the important techniques that are going to be used to circumvent those pitfalls. So that's the complete Gaussian elimination method, which approaches the problem by incorporating all of those pitfalls from the naive Gaussian elimination approach. So let's dive into the details of this complete Gaussian elimination method. First of all, let's see what are the problems that the naive Gaussian elimination approach faced. First of all, the zero pivot element. That means if the pivot coefficient becomes zero or very much small, then the approach is going to fail. Also, in each of the steps, the round of error is going to accumulate, and as a result the error might accumulate at the last stage and the result might get erroneous. And also we have seen that for ill-conditioned system, so for a very small amount of change in the coefficients, the result is drastically changed, and that is the case of ill-conditioned system. And the last one was the singular system. Whenever the two or three or many of the equations are similar, in those cases the number of unknown variables will be greater than the number of equations. So that was the case of singular system. So all of these four systems for pitfalls, because of these pitfalls, the naive Gaussian elimination approach was a very much risky method to apply. So we need to find out some of the techniques to circumvent these pitfalls. So that's the main purpose of complete Gaussian elimination 1. So first of all, let's look at how we are going to solve the zero pivot element problem. So the zero pivot element problem occurs whenever the pivot coefficient becomes zero or becomes very small. If it is zero, the pivot coefficient becomes zero, then we will have an infinite value and the Gaussian elimination approach will fail. But if it is the pivot coefficient is very small, say for example 0.000001, then dividing by that value we will have a large number, and it might happen that in that case that the number of numerical values will not be able to be stored in the computer memory, and in that case we will have the round of errors or the truncation errors. So that's why we need to remedy for the zero pivot element or small pivot element. Okay, so how we are going to circumvent this? For example, let's say we have this system of equation. There are three equations, and if you start the naive Gaussian elimination approach, the first pivot coefficient will be 0.0003. This is a very small value. Okay, this is one example of the zero pivot element or small pivot element. Although the pivot coefficient is not zero, but it is very small, so dividing by this value will result in a large number. So how we are going to circumvent this? A common approach is that we find the largest coefficient from the first column. Okay, in the first step we are going to find the largest coefficient from the first column. What is the largest coefficient? It is 1 in the second equation. So we are going to modify this original system in such a way that this largest element becomes the pivot coefficient. So what we are going to do, we are going to make the second equation the first one. So we are going to replace the first equation by the second equation, and we are going to take the first equation to the second place. Okay, so this is the approach that we can use. So now if we start the Gaussian elimination approach, we have the pivot coefficient 1, and by dividing this one value it will not cause any problem, because dividing by 1 is actually have no effect on the division. So in this way we can use the pivoting this is called a partial pivoting, because in one step we are just finding out the maximum coefficient from that column. Okay, in the first step we are finding the maximum coefficient from the first column. In the second step we are going to find out the maximum coefficient from the second column. So we are just using the column values, and that's why it is called partial pivoting. Okay, another one is complete pivoting. So in that case we are not only going to search for maximum element in the column, also we are going to search all of the rows and columns in the coefficient matrix. So in the first step, let's see what is the maximum coefficient that is occurring here, which is 3. So we are going to interchange these two columns. That means we make the second column the first one and make the first column the second one. So in that case, our modified system will look like this. Now in this system, in this modified system, look at this. We have the first constant, unknown variables are x2, and here we have the unknown variables x1. So we have changed the arrangement here, and we have changed the arrangement of the unknown variables here, so to make the pivot coefficient the maximum one. So how we have got this maximum element? We have searched the entire coefficient matrix for the maximum element, and that's why it is called complete pivoting. That means we are searching the complete coefficient matrix to find out the maximum element, and then we make the maximum element the coefficient, the pivot element, the pivot coefficient. So after modifying this value, modifying these equations, we can start the Gaussian elimination approach. Now let's see here, the coefficient is very much small. That means not very small, but it is very much within the range. That means it is not 0, and also it is not very small. As a result, the Gaussian elimination method will work pretty fine. But there are some problems of complete pivoting. To implement the complete pivoting, it is a challenging task, because you have to search all the coefficients in all of the steps. As a result, it becomes very much complex. So in most of the cases we actually use the partial pivoting. We do not use the complete pivoting. We try to use the partial pivoting. So pivoting minimizes the round of error too. Why? Because if the pivoting element, the pivot coefficient was very small, then dividing by that coefficient will result into a large value, and as a result there will be round of errors. But since after modification the pivot coefficient has become a finite value, a very much large value, so dividing by these coefficient there will be no case of round of error. So at least the round of error will be minimal. So pivoting actually minimizes the round of error. And also remember, we use the partial pivoting in most of the cases. Complete pivoting is a challenge. So let's look at an example how we can use the pivoting to circumvent the zero pivot problem. So we have this system of two equations. Look at this. So if we start this system, if we start the Gaussian elimination from this system, we will have the pivot coefficient in the first step to be 0.0003, which is a problem, because by dividing this small value we will have large values in the resultant values. So we have to use the pivoting, partial pivoting to solve for this zero pivot or small pivot problem. Remember, the exact solutions are given, which are x1 equal to 1 by 3 and x2 equal to 2 by 3. These are the exact solutions. So we are going to use the Gaussian eliminations to find out the resultant unknown variables, which must match these two values. So let's look at the solution. We are not going to see the details because we already know how to use a Gaussian elimination method. So that's up to you. So just remember, we are going to solve this problem with the pivoting. That means we are going to find out the maximum element from the first column, and we are going to interchange those two equations to make the pivot coefficient a large one. So there are two tables that are shown here. The left one is without partial pivoting and the right one is with partial pivoting. What are the results? Look at this. although the pivot elements is not 0, but it is very small. As a result, whenever we are not using the partial pivoting, we are going to get to the original results at the 7th, at the very far. That means we have to consider a large significant figures to get to the original result. Okay, so if we consider 7 significant digits in all of the steps and we use the without partial pivoting, we will get a very much good result with a 0.1% error, and we get the result whenever we get the 7 significant digits. But whenever we are using the partial pivoting with just 3 significant digits, we are going to get the result which have the same error with the without partial pivoting. That means in this case, without partial pivoting, we get the same result using 7 significant digits, but with partial pivoting we get the same result with just 3 significant digits. So that's the burden is reduced a drastic amount. So in the first case we would have to use 7 significant digits in all of the steps, but in the second case we have to consider only the 3 significant digits. So this is the case that in 0 pivot element, whenever the pivot element becomes very small, if we use the partial pivoting or complete pivoting, we will get the same result with much less effort. Okay, the round of error will be reduced. So that's the benefit, that the pivoting reduces the round of errors. So the first two problems of the naive Gaussian elimination, which are the 0 pivot element or small pivot element and the round of errors, those have been solved by using the pivoting, partial pivoting. So partial pivoting also reduces the round of error. And the third pitfall of the naive Gaussian error, the naive Gaussian elimination, was that for ill-conditioned system, the Gaussian elimination approach fails. To circumvent this, we can use more significant figures in our calculations to get the results of ill-conditioning system. So what is the resultant decision from all of these discussion? The more significant figures we always use, the more precise result we always get. That's the thing we have been following in this course, that the more significant figures you use, you get more precise results. So in this case, in Gaussian elimination, if the system is ill-conditioned, please try to use more significant figures in your calculation. As a result, you will get to the original value more easily. Also, there will be some cases in practical scenarios that some of the coefficients are much larger than other coefficients. Look at this. In this system, the largest coefficient is 30,000. Okay, and the smallest coefficient is 0.5. So there is a large gap between the numerical range of these two values. As a result, whenever you calculate with the Gaussian elimination method, you will get that some of the results, some of the numerical values are very large and some of the numerical values are very small. This is a very problematic and scenario. So what we do in such cases, we divide all the coefficients and constant terms by the largest element of the matrix. So in this case, in the whole system, the largest number is 30,000. So we divide all the coefficients and constant with this value 30,000, and as a result the system look like this. Now see, the values are very small and within the range. As a result, the values that you are going to find out will be within the range. As a result, it will be very much easier for you to calculate with small values. So you can use this approach whenever you have large numbers in your system. And the last pitfall that the naive Gaussian elimination approach faced was a singular system. So in a singular system, two or some more equations are similar. So this is actually a human error. So what we can do in your program, in your computer program, you can keep a checkpoint at the start of the code to see whether the system is singular or not. So to find out whether a system is singular or not, a common shortcut is that you use the determinant of a system. That means you take all the coefficients of the unknown variables and determine the determinant of that coefficient matrix. And if the determinant is 0, that means the system is singular. And if the determinant is not 0, the system is not singular. So this is a shortcut to finding out whether a system is singular or not, to find out the determinant of the coefficient matrix. So in this lesson we have learned that in some cases we can circumvent some of the pitfalls of naive Gaussian approach by partial pivoting or using a division method to divide all the coefficients by the largest number in the system. So these are some of the remedies that we can use to circumvent the pitfalls of naive Gaussian elimination. So that's the complete Gaussian elimination. We use the partial pivoting, and that's the main concern is here. We use the partial pivoting. Partial pivoting is very useful. And the second remedy we used was the scaling. That means when we had large numbers in the system, we can divide each of the coefficients and constant by the largest number of the system. As a result, all of the numbers will be within the range of 0 to 1, and it will be very much easier for us to calculate. Also, we can use a checkpoint in our computer program to find out whether a system is singular or not. So that's the third solution: partial pivoting, scaling, and singular system detection through code. And also, if you have a ill-conditioned system, you can use large significant numbers. That means many significant numbers in all of the calculations to circumvent the round of errors and the ill-conditioned system. So please try out the MATLAB code that I have attached with this slide to implement the complete Gaussian elimination method. To use the pivoting, I have implemented the partial pivoting approach. So please go through the details of the code and try to understand how the partial pivoting is implemented there. So it will be helpful for you to understand the main thing. In the next lesson, we are going to learn about another extension, or if I say another variation of the Gaussian elimination method, which is named as Gauss-Jordan method. So that's an extension for the Gaussian elimination method, and we are going to cover the details of that in the next lesson. So till then, thank you so much.